Next, we study the gamma distribution. Remember, we studied beta distribution, then gamma distribution. And the gamma distribution is defined by the following density function. So the density function is beta, alpha, and gamma function, and x, alpha minus 1, and beta x. And this random variable takes the value greater than or equal to 0. Okay, so this is the range of the random variable following the gamma distribution. And alpha and beta are parameters which are positive, both positive. Okay. And alpha is called shape parameter. They can be different names, but often called shape parameter, and beta is called the rate parameter. Okay. And when a random variable x follows this gamma distribution, we write x follows gamma with parameters alpha and beta. Okay. Let's see some examples of this density function. So here I took this figure from Wikipedia again here, and the density function of gamma distribution is this, as I have defined right now, but it can be also often expressed as this. Instead of alpha and beta, we can use theta and k. Actually, this k is same as alpha, but theta is inverse of beta. It's reciprocal of beta. So, okay, here are examples. When k is 1 and theta is 2.0, that means alpha is 1 and beta is 0.5, then we have this curve. Okay, does this look familiar? Familiar? Actually, in this case, this gamma distribution is an exponential distribution. It's the same as the density function of an exponential distribution with the parameter 1 over theta, so with the parameter of beta. So if you look at this definition, when alpha is 1, okay, then alpha minus 1 is 0, so this term will disappear. Okay, so what we have is this part, and there are no x's here, so this is essentially, it is an exponential distribution with parameter beta. So gamma distribution is a generalization of the exponential distribution. Okay, and when k is 2 and theta is 2, then we have this curve. Let's see this curve. So in this case, the density becomes 0 when x is 0. Okay, then it increases up to some point, then starts decreasing, like similar to exponential distribution. And when k becomes large, for example, let's see, when k is 5 and theta is 1, then we have this green curve like this. So we can see the curve shifts towards the larger value of x. And when k becomes even bigger and theta becomes smaller, so in this case beta is 2, we have, let's see, we have this curve, black line, like this one. Okay, when beta is less than 1, alpha is less than 1, alpha OK is less than 1 in this case, then we have this curve. Okay, so the density diverges when x goes to 0. Okay, at this point the density diverges to infinity. But still, if you integrate this from 0 to infinity, then of course it's less than, it is 1 because it's a probability. Okay. Actually, the relationship between exponential distribution and gamma distribution is deeper than that. Okay, to see this, let's see, we have two exponentially distributed random variables. So exponential, let's say lambda. So this x1 and x2, they are independent and identically distributed according to the exponential distribution with parameter lambda. Okay, and suppose both of them have the same density function because it's exponential distribution with the same parameter. The density function for x1 and x2 is this, same. Now, we define a new random variable by adding these two random variables. Okay, then what is the density function for y? Okay, let's say density function for y, let's write it g as g. Okay, density of y. Okay, so what is this function? To answer this question, let's calculate this probability. So this small y is a constant. So this is basically the cumulative distribution function for y. Okay, since x1 and x2 are exponentially distributed, they are non-negative, so y is also non-negative, so we integrate from 0 to y. Okay, and if we assume the density is g, then it's written like this. But g has actually two random variables inside it, but they are independent. So this g of s can be written as, maybe I should write, let's see, from, okay, 0 and x1 plus x2 less than y, and f of x1 and f of x2 dx1 dx2. So this is a double integral. Okay, so but although we integrate from y from 0 to y, in this case we split this y into this sum of two exponentially distributed random variables. So the density function is just product of these two, but the range of integration here is this. Okay, so we keep this restraint while integrating. Okay, how can we do this? So if we consider two-dimensional space, so let's say x1 and x2. Okay, so what is the region where this is satisfied? Okay, this y is a constant. x1 and x2 are variables. Okay, and of course x1 is greater than 0 or equal to 0, and x2 is also greater than or equal to 0. Okay, so this region is actually this region where this line is this line, x1 plus x2 is equal to y. Okay, in other words, if you want, x2 is equal to minus xy plus y. So that means this intercept is y. Okay, and actually this intercept also y, and this is 0. So what we want to do is integrate this function over this region. Okay, so that's what we want to do. Okay, we want to evaluate this integral, but there are two variables. So there are two things that are moving, and that's hard to deal with. So it's easier if we fix one of these variables. Let's say we fix a value, the value of x2 at this point, and consider only one-dimensional integral over this region. Okay, from here to here. So this value is, since this line is x1 plus x2 equal to y, so this value here is y minus x2. So it's easier to integrate. Okay, so let's see. This integral is equal to, so we fix the value of x2 and integrate from over x1 from 0 to y minus x2. So in this case, the variable is just x1. And we move the value of x2 from 0 to y. Okay, so from 0 to y, we move the value of x2. So first evaluate this part. But if you look at this, this is just a cumulative distribution function for x1, right? From 0 to y minus x2. So that will be cumulative distribution function. And this one comes here. And since the density function is this, it's an exponential distribution, so the cumulative distribution function is 1 minus exponential of minus lambda x. So this comes here. And the density function comes here. So just substitute these functions into here and here. And after some calculation, the result is one minus lambda y minus lambda y exponential minus lambda y. So this is the cumulative distribution function for y. Let's write it large G y. So in order to obtain the density function for y, we differentiate this function with respect to y, which would be, I skip the details, and should be lambda squared y exponential lambda y. So this is ugly. So, but what is this density function? This density function is the density function for gamma distribution with alpha equal to 2 and beta equal to lambda. So after all, this random variable y follows a gamma distribution with parameters 2 and lambda. And in a similar manner, if x1, x2, and up to xn, they all follow the same exponential distribution, then if you define a new random variable as the sum of all these exponentially distributed random variable, then y follows gamma distribution with parameters n and lambda. So you should prove this. Okay. And just for the sake of convenience, I just write the result of this calculation. For gamma distribution with parameters alpha and beta, the expectation value is alpha over beta, and the variance is alpha over beta squared. Now, you know that when alpha is 1, a gamma distribution is just an exponential distribution. So just put alpha equal to 1. Then you have the expectation value of expectation value of exponential distribution with parameter beta as this, and variance is 1 over beta squared. Okay, and if you compare this with this, and especially given this result, here alpha becomes n, right? So after all, the expectation value of the gamma distribution is alpha times the expectation value of the exponential distribution. And same for the variance. It's alpha times the expectation value of the exponential distribution. And you've seen something similar before, right? A binomial distribution is expressed as a sum of random variables that follow the same Bernoulli distribution. And the negative binomial distribution, its random variable, is expressed as a sum of random variables that follow geometric distributions, and so on. So if you have one distribution, and and if you have a set of independent and identically distributed random variables, and take the sum and calculate a new random variable, then you always have this kind of result.